Okay, very good morning, all of you. I hope all of you are enjoying the beautiful city of Leon and the program so far. My name is Sandeep. As you all know, today is the last day of the conference, and it gives me great pleasure to introduce our keynote speaker for the day, Tara Sainath. Tara is a distinguished research scientist at Google DeepMind. She has done most of her education at MIT, bachelor's, master's, and PhD. And she has spent about 5 years or so at IBM Research before she joined Google DeepMind. So Tara has been contributing to the Signal Processing Society, IEEE, part of editorial board of IEEE Transactions on Speech and Audio Signal Processing. And she has won several paper awards, particularly in the SPS Society, Signal Processing Best Magazine Paper Award 2022, 2021 SPS Industrial Innovation Award. And from what I gather, she has made impactful contributions to speech and speaker recognition and using deep learning techniques. And recently, she's been involved in all the activities around LLMs within DeepMind. So without further delay, let us all welcome Tara to deliver this keynote.
Thanks, Sandeep, for the warm welcome, and thank you for the organizing committee for having me here. So today I'm going to talk about end-to-end speech recognition over many years at Google, really looking at our journey from research all the way to productionization over the past 8 years. And as I said, I'm going to go through years of research conducted within audio teams around Google, moving towards having audio processing done completely within neural networks, landing these models into production, most primarily focused on device, and then more recently looking into extending the size and language coverage of these models, and finally scaling up these models to introduce more audio to X capabilities, looking at things like Gemini that I'll talk about towards the end. So just to sort of set the stage, because not everybody here has a speech background, I want to first go into what is at a very high level, what is the speech recognition problem? What are we trying to solve here? So we're given a series of acoustic observations. We can think of these typically as some Mel filter bank frequency features through time. And the speech recognition problem is to find the best set of recognized words, W, and we can decompose this with Bayes' rule, where P of O given W is what we call the acoustic model, and P of W is called the language model. So let's take a look at this problem in a bit more detail. So this is typically how a conventional speech recognition system works. So you take your input audio, raw waveform, you have a feature extraction phase where you convert this into some time frequency representation, typically Mel filter bank coefficients. And then you have an acoustic model which maps your features to some set of subword units. And typically we don't have enough coverage in our data to represent all triplets of, say, phonemes. So we have to do some sort of special clustering to do this. Then we have a lexicon, which maps phonemes to words, and a language model, which gives the probability of words following other words. So I think the main thing I want people to take away from this slide is that each module here is completely independent of the other modules. It's often trained independently on very different data sources. And there's a lot of handcrafted knowledge which goes into each of these submodules. And so for many years, this made the speech recognition problem very, very complicated, where many people had very specific domain expertise in maybe one of these submodules. So what we have been looking at for numerous years is, can we have a much simpler solution that'll say, I want to take the sequence of acoustic features and map them directly to words? And that's really what we mean by end-to-end. So another thing we want to keep in mind is that in a conventional system, each component is separately optimized. So nothing in the conventional model is trained to optimize what we care about in the end, which is in speech, it's called word error rate. So within this end-to-end framework, we want to look for a solution where we train the model to optimize the actual objective we care about in the end, not optimizing each individual submodule separately. So pictorially, this is what we're after. We want to take all of the components of a conventional system, the acoustic model, the pronunciation model, the verbalizer, the LM, and represent this by one neural network that goes from features all the way to words. And why do we want to do this? As I said before, simplicity. It's much simpler to have one model do this all rather than having separate components that require a lot of domain-specific knowledge. The second is joint training. We felt that with one neural network to optimize everything jointly, it would actually have better performance than optimizing all these modules separately. So here starts, around 7-8 years that we've been working on this within the Google Brain, DeepMind, speech, hardware teams at Google. So I'm going to describe, this journey in the subsequent slides and how each iteration of the model improved on previous iterations, providing new capabilities and features and leading us all the way to this LLM era today. So conventional speech systems have been developed for decades. It's not really easy to replace this with a single end-to-end model. So there's been a lot of work in the literature that contributes to this direction. So let's just take a look at this in more detail. The first effort that worked towards such end-to-end models is called CTC, or Connectionist Temporal Classification, and this was developed by Alex Graves and others. In the original paper, it's basically used as an acoustic model that converts speech features to some subword unit. So it was not really end-to-end. You have to combine it with an additional language model. So CTC produces the probability for each label at a frame, given some input feature X. And the key to note here is that every output is independent of all other frames. So this will be really important to remember when we look at how CTC works for speech recognition. So the main contribution of CTC is that it introduces this notion of blank symbol and maximizes the total probability of the label sequence by marginalizing over all possible alignments. And this removes the need for the frame-level alignment when you train such models. So the best CTC models were used as acoustic models. And that's because CTC has this frame independence assumption I mentioned. That means the network outputs are different, at different frames are conditionally independent. There has been some work looking at CTC for end-to-end systems. For example, based on the original CTC method, Alex Graves and colleagues developed further character-based CTC methods to remove the need for pronunciation models. And there's also been work at looking at CTC end-to-end, directly outputting words with longer subunits. But one thing that none of these methods have been able to get rid of is you need to have a language model, and I'll show that in subsequent slides. The performance is much worse if you don't have a language model because of this frame independence assumption. And so it's not really suitable for practical usage. So now let's look at an alternative method, which is an attention-based encoder-decoder model. And this doesn't have that frame independence assumption that CTC has. So motivated by use in NLP tasks, this attention-based encoder-decoder model was adopted around 2015. And this encoder, in this model, we can think of the encoder like a conventional acoustic model. It takes inputs and it transforms the speech features into some higher level representation. We can then think of the attention model or as an alignment model. It identifies what frames in the encoder space are important to pay attention to when we're predicting some certain subword unit. And finally, so we can think of the attention model sort of like the pronunciation model. And finally, the decoder model is similar to a language model. It's an autoregressive neural network which takes the previous subword unit you're predicting and predicts the next unit. So most importantly, this whole model is optimized jointly. So given input features, you predict the output subword units directly. So years ago, we looked at how did these two methods that I just touched on the previous slides, both the CTC model and the attention-based model, how do they compare to a conventional model? And here, when you say online and offline, offline means the model is not streaming. You have an encoder which is full context, so you see the whole audio, and your network operates bidirectionally, then processes the audio and gives it up to the language model. And online means that LSTM or conformer is streaming, so it operates in a causal way frame by frame. We'll get into why online is important in another section, but that's what the difference is here. So the first thing that you can notice is that the CTC model has a word error rate on a voice search task. Word error rate here in our definition, lower is better, of around 50%. That's a lot higher than the conventional based model, either online or offline. And this is because, what I was alluding to before, because of the frame independence assumption, if you have this model go directly from audio to characters without any language model, it's very, very poor. Now you can see the attention-based model is a lot better because it has the autoregressive decoder. The LM is sort of modeled within the network itself. It has a much stronger language model. But you can see that it's still much worse than the conventional model. So we started this, what I'll call hill climbing approach, to sort of bridge the gap between the attention model and the end-to-end model. And there was a few key things that we had to really fix to get this to work. The first is, when we process, after we see the encoder features, we have to compute attention on these to see what we should pay attention to when predicting the current subword unit. So typically we used to use a single attention head, and we swapped this to using what we call multi-attention. So here's an example of using 4 attention heads. So the figure on the right is single attention, and the red figure on the left is using multiple attention heads. So what you can see is that the model now looks at multiple points in the past in order to predict the current subword unit, and this kind of makes sense with when you do speech processing. And what you can see is empirically the model is looking towards previous frames when predicting this. A second technique that was really important is looking at longer subword units that are longer than graphemes. So typically, if you have a longer subword unit, like all the way to a word, you have a much lower perplexity in your language model. And usually this gives an improved efficiency in the decoder because you don't have to clock the decoder as often. Now, we'd like to go all the way to words, but we don't have enough coverage in our data. So our training data, let's say, has 100K words, but the actual word vocabulary we want to support is close to 4 million. So it would be very difficult for us to model all the way to words. So we take some intermediary, which we call word piece units. And here, a word piece model, you take the phrase good afternoon, and you train this on all of your text data. You train a word piece model to maximize the LM likelihood on this training data. Once you train it, it's position dependent. That means any word has a deterministic decomposition to word piece units. And within the word piece units, you also have a set of characters, so all the units can back up to characters, so there's no other vocabulary words. So here's an example of good afternoon, and it's transcribed, it's decomposed word piece decomposition. And you can see the underscore basically is indicating the space, so the space is modeled within the word itself. Okay, a third change we did is we changed the optimization. So although end-to-end models are trained to output speech units and the target word sequence, the objective is actually to maximize cross-entropy. So this is the log likelihood of the labels Y, which are subword units, word pieces, given the training data. So we actually don't optimize it for word error rate. But in practice, word error rate is the metric we care about. So we came up with this new optimization called minimum word error rate training. So what you do here is the first equation gives the cross-entropy loss. So this is basically you are training to maximize the probability of predicting a subword unit given its history, Y, and it's the input audio sequence X. So that's really not maximizing word error rate. So what you can do is you can train your model with for some amount of time, maximizing cross entropy. When your model gets to a good space, you can start running it as a beam search. Once you run it as a beam search, you can calculate the errors in that beam. And you can weight the output hypothesis by the number of errors, and there you can basically model the expected number of word errors. This is what we call minimum word error training, so that you are more closely asking the model to optimize the metric that we care about, which is word error rate. So when we put all of these different changes together that I mentioned before, and these were the main ones, that model I showed you before, the conventional server-based model, which is around 7.2 gigabytes, has a word error rate of 6.7. And in comparison, our attention-based model is almost 18 times smaller and has a word error rate of 5.6. So it's about 16% relative improvement. So this was the first time around 2018 that we really ever saw that these models could come close to a conventional server-based model. But the problem, of course, is that the attention-based model is not streaming. So as I mentioned before, you see the full context of the encoder before you start computing the attention, whereas the conventional-based model is streaming. And streaming is very, very important for Google products. So let me get into why and how we fix that. So streaming speech recognition is a very key component of the Google speech recognition system. What this means is that when you speak, you want to recognize the audio as quickly as possible, endpoint, finalize the recognition, and then take an action by fetching the search result. So when you speak, you don't want to wait, 2,000 milliseconds before you get the response from the server. That's not a great user experience. So we need to stream everything to make sure that when you speak, you get your answer right away. And this is really, really critical for a good user experience. So now, how do we make a streaming end-to-end model? So previously we saw, CTC is actually streaming because you take one input feature and you output a label for each of those features. You have either a subword unit or blank. But what we saw is that model had really poor performance without a language model. So we proposed what we called a recurrent neural network transducer to address that problem. So that model works like follows. You have an encoder network, which is like an acoustic model. This is a set of recurrent layers, very similar to the attention-based model I showed before. So you take your input features and run them through a streaming encoder, and you get some higher level representation. Now you have a prediction network, and that is similar to a language model. So you take the previous prediction and you run it through a autoregressive neural network to get some higher level representation. And now what you do is you have a joint network that combines your acoustic and language model predictions. And then you feed this to your softmax. So at every frame, you have your input feature and your previous prediction, and you get an output. Either the RNNT will output a label or it'll output blank, just like in CTC. You can see the difference now is that you have this prediction network. So the autoregressive component of what you're predicting is now fed back into the network. And that's the big difference from CTC. This whole thing is optimized jointly. You don't need any alignment, and it's streaming. So that means for every frame, you get an output either blank or a label. So endpointing is this problem of after the user speaks, you want to close the microphone as soon as the user has stopped speaking. And this is really critical for good user experience. A very common approach is you run a voice activity detector. So you have this little neural network that sits independently of this model that just looks for big changes in the energy to detect if the user is done speaking or not. Now, we've just spent 20 or so minutes talking about why we want to do joint optimization of everything. And a voice activity detector is not jointly optimized with everything else. So we wanted to do this a little bit better. So the high-level notion is, when you're speaking, if I say, what's the weather in, I'm not done speaking, so the model should know that. But if I say, what's the weather in Boston, it's a complete thought, and the model should be able to better detect semantically that I'm done speaking. So what we do is we train an endpointer where the neural network itself, the RNNT model, is going to emit a token called end of sentence. And this is called a semantic endpointer, and it should indicate that the user is done speaking just by this tag, and the microphone will close once we've emitted this tag. Okay, so how does this end-to-end semantic endpointer compare to a voice activity detector? So first, let me go through metrics. So the two metrics we report is word error rate, here lower is better, and then we report what we call an endpointer latency. That's the latency of after the user has finished speaking, how long did it take to actually detect an endpoint? And you want this number to be as small as possible. So typically when you're doing endpointer optimization, you're sweeping out some ROC curve and you're trying to find the point where you have the lowest word error rate and the lowest latency. Here what you see is that the first line, the RNNT with the external voice activity detector, has a word rate of 7.4 and has an endpointer latency of 860 milliseconds. So that's very slow. Whereas the RNNT model has a much better word error rate and actually has almost a 90 millisecond latency improvement. So that again tells us that doing this joint optimization of folding the endpointer into the network is actually better than separate. Now, one of the problems with RNNT is that it's streaming. So that means it would always lag behind the quality of an attention-based model like listen, attend, spell. So to really improve the quality of our model, what we proposed is to use listen, attend, spell as a rescore. So the way we do this is as follows. We take our encoder that's streaming, given our input feature X, and then we go through a first pass RNNT decoder. So we quickly emit words to the screen. And then what we do is we stick some additional encoder layers on top of the shared encoder. And once we've emitted all the words to the screen, then we have the full encoder sequence in front of us. We can run a second pass attention-based model. And if we do this as a rescorer, so we take the first pass hypotheses from RNNT, usually we have about 8 of them, and we rescore this with the second pass, that would give us the benefits of seeing sort of full context with the attention-based model, but it would fit within the latency constraints because rescoring is not that expensive, especially if you have all the hypotheses in the beam. So you can see that if you look at the first line, which is your RNNT first pass model, has a word rate of 6.8, and you get around a 10% improvement by doing this rescoring. So this is a technique that allowed us to take advantage of seeing full context, but still have this notion of streaming first pass results to our screen. All right, so if we put everything together, and here the numbers have changed from the previous section. So the first line is sort of a state-of-the-art conventional model where you have a first pass and then a second pass 80 gig LM. And so that's a word rate of 6.6 and endpoint latency of 870. And you can see that the N10 model is more than 480 times smaller, has almost 10% relative improvement in word error rate, and is about 90 milliseconds faster. So this is a model that we considered launching on device for Pixel 4. And this was the first time that we'd ever developed such a model that surpassed server-side conventional in both quality and latency. And we launched this in Pixel 4. And here's a review from The Verge. It says, you can ask your assistant to do anything on your phone, and they'll do it nearly instantaneously. It's much faster, and you don't really need to rely on Google Server. So this model is sitting directly on the phone. You can disconnect from the Wi-Fi, and you'll still get speech recognition. Here's an example. This is Gboard. The demo on the left is doing the server-side transcription, and on the right is on-device, and you can see how much faster the on-device model is. Okay, I'm going to skip this demo. We have more demos coming, but obviously the slides are shared, but this is a demo showing that model, but we have even more demos coming. So to summarize high level, the first part, I talked about various aspects of end-to-end models, and even though these models have launched in some products now, such as Pixel 6, there still remains a lot of challenges. One of the biggest challenges is that I'll touch upon now is we are training our language model jointly with everything else. So that means you're only training it on the number of acoustic text pairs that you have, which is a fraction of the amount of text data we have. So that means we actually have a pretty weak language model. So if you try to give the model really obscure phrases, it just doesn't pick it up. I think at some point there was a presidential candidate, Pete Buttigieg, that was running in the US, and the model would not pick up his name. But the conventional models did. So we'll see in the next section how we address some of this. So we started this around 2001, and this was the launch for Pixel 6. And we had a few goals in mind. First, we wanted to have a model that had improved word error rate over a conventional model, both in general search traffic and also in these really long tail phrases. We wanted the model to be faster, not only in terms of the endpointer latency that I showed, but also in terms of the computational latency. And we really wanted the model to consume low power, taking advantage of the specific tensor hardware that was available on Pixel 6. Okay, so we made a few changes. So the first is we changed the type of encoder we have. Previously, we were using LSTM layers. So these layers are sequentially dependent in time. What that means is you have to compute the activation at a specific time frame before moving forward to the next activation in time. And this also hurts TPU latency as well, because you have to wait at every point in time. You can't sequentially parallelize this. Furthermore, while LSTMs do help with vanishing gradients, it doesn't completely go away. And we did notice these models didn't do well for very long utterances. In comparison, a conformer or transformer-based architecture allows you to compute multiple activations in parallel. And so this is much more TPU friendly, and it's also better for long form quality. Secondly, the Pixel 4.5 decoder was an LSTM. It's around 30 plus million parameters. That means it can't fully fit in the SRAM of the TPU for Pixel, which is around 6 megabytes. So we needed to shrink the decoder somehow. So what we did is we looked at replacing it with a simple lookup table. So this means given the previous two predictions of the network, just do a simple embedding lookup to figure out the next label. By doing this, you can fit the entire decoder into 2 million parameters. Then you can fit it directly in the SRAM, and you don't have to do this latency transfer between CPU and TPU to fully compute the decoder. So this gives us around 30% speed up in computation, and we took no accuracy degradation there. Third, the previous models I showed you were running this first pass streaming RNNT, and then a rescore with some attention-based model. So we know that this has the drawback that the quality of the model is limited by the hypotheses from the first pass. So alternatively, you would like to run the second pass as a beam search, but you want to make sure when you do that, you don't incur too much latency. So we introduced this model called cascaded encoder. So specifically, you take a first pass model that is fed to a causal encoder and then an RNNT decoder. And then what you do is you have a set of non-causal encoder layers that sit above the causal encoder. And these are conformer layers that just have, let's say, a 1 second look ahead. So you delay this by 1 second, and you feed it to the same RNNT decoder. So what this allows you to do is you quickly show the first pass result to the screen, and you delay a little bit to show the second pass result, but not enough to incur too much latency. So the total final latency is still pretty reasonable. So this allows us to run a 2-pass model actually as a beam search. And finally, as I mentioned before, there's a lot more text-only data compared to audio-text pairs. So we want to take advantage of this to improve the quality on long-tail named entities. So the most common way of incorporating knowledge is via shallow fusion. So you take the score from the end-to-end model, that's P of y given x, and you interpolate this with some external language model. So this is not really mathematically correct, So some of our colleagues introduced what they call a hybrid autoregressive transducer, and that's a better factorization to integrate a language model. So what you do is you take your score of P of y given x, and now you approximate the first two terms now as P of x given y. So this can be written as an internal language model that you subtract out, and then you add the external language model score. So once we do this way of incorporating a language model, we look at two ways to improve long tail. The first is what we call contextual biasing. We build a small finite state transducer on phrases that we know are going to be commonly said. Let's say contacts in your phone, or song names or apps that you commonly call in your phone, or if you're in a specific geographic location, you can pull a contextual biasing FST depending on the location you're in, a geographical one. The second is to just train an external neural language model on the 100 billion text utterances that we have, and then just fuse this in and look at rescoring the first pass hypotheses during the beam search. And we did rescoring basically because it's much more efficient computationally. Okay, so this right here shows 3 columns. The first is your classic server word array. The second is the Pixel 4.5 LSTM model, and the third is this conformer cascaded encoder neural LM architecture I just talked about. And what you can see across a variety of search test sets, both clean and noisy, and very much related to search and the assistant, you can see that the Pixel 6 model is the best speech recognition system that Google has ever built. It's significantly better in quality than the other two. Now, if you look at these a test set for really obscure phrases, this is a biasing test set for contacts. This is seeing how well we do in detecting certain obscure names on your phone, on your contact list. Media, so this is detecting song names. In apps, how well do we open different apps that somebody has on their phone. So the way we do this, as I said, is we build this contextual biasing FST on phrases as well as a bunch of distractor phrases as well. And so what we're seeing here is the word array. The first one, if you look at the first column for classic, the 9.7 is when you do the biasing, and the parentheses is just without the biasing. So you can see how important biasing is. And the main thing to take in mind here is that, again, if you look at those 3 columns, classic is the first, the Pixel 4.5 is the second, and the Pixel 6 conformer is the third. You can see significant improvements in the biasing quality across all verticals. And of course, we also ran what we call a side-by-side on live traffic, comparing the on-device model to server. So what we did is we took about 500 utterances, and we ran them through both models, and then we had raters rate them as a win, a loss, or a neutral. So a win here means that the on-device model is better than the server, loss means the other way, and neutral means they're both about the same. And this p-value is the statistical significance of the word array change. And the impact score is what percentage of the traffic was actually changed by this. So typically 1 e to the -2 is considered a huge impact. So what you can see is we have a win-loss ratio of 120 to 36. That's almost 4 to 1. So that means this model is much, much better than the current server-based model across on live traffic. And so here's a video on detecting rare words. So the left is, they're saying Bexar County, Texas. The left is the Pixel 4 model, and the right is the audio is buffered. Let's do it again.
Bexar County, Texas.
So I'll play it again, but you can see the left side does Bexar County as B-E-A-R, but it's actually Bexar, and the Pixel 6 model gets it right.
Bexar County, Texas.
All right, and I'll play a video, hopefully this streams properly. This shows some of the highlights of the Pixel 6 model.
Tensor is unlocking so many helpful camera features in Pixel 6. From improved video quality, to face unblur, to motion mode. We think it all adds up to Pixel 6 being the most advanced intelligent smartphone camera. Next up, let's talk about how Tensor is making typing much faster on Pixel. Obviously, speaking is the fastest and most natural way to go, but today's voice input systems just haven't been up to the task. First, understanding the nuance of human speech is really a hard problem, with challenges that are unique to each person. It means understanding syntax, intent, and the context of your request, knowing the terms and names that are important to you, but potentially uncommon to others, understanding your accent and dialect, isolating your voice when there's background noise, and even hearing you correctly if your mouth is full. Google has led the industry for years with our natural language processing. It's why search queries are so accurate, and Google Translate is so good. Thanks to some outstanding work from our speech team, Pixel 6 has an on-device speech recognition model that can transcribe speech with incredible accuracy. And thanks to Tensor, it does it using half as much power as previously possible. It's the most advanced speech recognition model ever released by Google. With this new capability, we rethought the voice typing experience based on some key insights about how people write. Let me show you how it works. Hey Ronnie, are you still up for dinner tomorrow? With our friends? You can see how accurate the transcription of my friend's name is. Pixel is smart enough to take the hint from my contacts list, and the mic stays open while I tap to insert a clarification about who's coming. Pixel even automatically adds the right punctuation, so I don't need to specify where to put commas and question marks. Let's keep going. I hope you can come. Catherine is hosting this week. Of course, Pixel won't always know which Catherine I'm talking about, and the one I have in mind spells her name with a K. The language model also helps with transcription suggestions, so corrections make sense based on what you're saying. Historically, transcription suggestions have been the same ones designed for typing based on keystroke proximity. But that doesn't make any sense if you aren't typing with keystrokes. Now Pixel's model is phonetically based, meaning it suggests corrections that sound similar. So Catherine with a C becomes Catherine with a K, instead of catharsis, or cathedral, or whatever else you might have ended up with. And to make voice typing as fast as possible, I should be able to do more with my voice, including commands like clear or send. Pixel is smart enough to understand that I don't want those words in my message. I'm sure it's going to be great. Clear. I'm looking forward to it. Catherine has a really nice new place. Send. See how fast that was? Also notice that your phone remembered it's Catherine with a K, so you won't have to make the same edit twice. The model adapts to your usage. And watch this. The model also unlocks the accuracy of emoji transcriptions, which is so much faster than searching through little pages of icons. I think we're making homemade pasta emoji and ice cream emoji. Send. With the new speech model, typing with your voice is faster and easier than just typing with your fingers. Thanks to Tensor and these new breakthroughs, we can do all this on device without connecting to a server, so it's super fast and reliable. We really think it's going to change how you use your phone. Google's natural language understanding allows us to rethink phone calls, too. Call screen is great for shielding you from spammers. Unknown callers have to say why they're calling before you decide to pick up or hang up. It's a useful feature, and the Tensor speech models are making call screen even more accurate in Pixel 6. The next problem we wanted to solve is calling a business. It's been the same bad experience for decades, with hold music, the same long automated system saying, your call is very important. It's the worst. But Pixel 6 makes it so much better for you. Now, before you even place your call, Pixel shows you the current and projected wait times, so you can call when it works for you. And when you do call and encounter that endless list of options, like press 1 for branch hours and locations, you actually don't need to listen carefully and remember all the automated menu options. Google Assistant listens for the details and shows them on screen for you to tap. Of course, if you still find yourself in the hold queue, don't worry, Google Assistant will hang out on the line and listen to the hold music for you. It understands the difference between a recorded message and an actual representative on the line, and lets you know when a real live human is ready to talk. Tensor also dramatically improves translation features in Pixel, so you can interact naturally with people who don't speak the same language that you do.
Let's stop for now when we get there. So to sort of just summarize so far, the latest model that I showed is this, first pass RNT model with the second pass that's also streaming. It is, as you can see, it's the best model that we've released to date. It does well in both latency and quality on general search traffic and long-scale phrases. Brian mentioned something at the end, which was multilinguality, and that still remains a challenge. As you can see, every demo I showed you so far is in US English. So let's talk about how we scaled that up and solve that. So let me get into the universal speech model. So in a conventional speech system, when you want to do multilingual speech recognition, what you do is you build a separate acoustic language and pronunciation model for every single language. And then maybe you run on multiple languages and select based on some posterior or confidence score which one is the best. So you can see this doesn't really scale very well if we want to support hundreds of languages. There are other ideas on conventional code training, but in a pure sequence-to-sequence model, imagine what you can do is you can train the same end-to-end model on all of the languages together. This scales much better. So more specifically, what you want to do is in a convention model, you have N phonemes, lexicons, text normalization, and language models, and of course data, and you want to replace this by one model. This has a variety of advantages. One, of course, this is a lot simpler. It's just one model, just trained on all the data. And we believe that if you do data sharing, this will actually give you improved performance on languages. Specifically, you're sharing amongst dialects and model components. As we've seen many times in this talk, joint optimization is going to be much better. And then this is a whole lot simpler in terms of infrastructure. So our task here is to say, let's take around 85 languages, which is around more than 660 million supervised and unsupervised hours in YouTube. And let's train a massive model on the order of billions of parameters. And let's see how well such a model can do on speech recognition. And we're really after three tasks. One is to see how well this does on in-domain tasks, but also how well this generalizes to new languages and how well it can be used as a backbone for upstream tasks. So what we did is we trained a universal speech model on these 85 languages. And here, this is a 2 billion parameter RNNT model. And what I'm quoting is results compared to Whisper. The blue here is the universal speech model. The green is Whisper on 3 different categories. The first one you can see is on 18 head languages. You can see the USM is much, much better than Whisper. And then on an internal in-US task, you can see that the USM is better than than a conventional model on this state-of-the-art internal task. And you can see even on 73 languages, the word area is averaged to be about 25%. So it's not really severely broken on any language. So we are able to train these massive models, RNNT models, on all of our 75 languages, and it seems to have relatively decent performance. So now one interesting thing we wanted to look is how well does this scale up to new tasks? So to measure the performance of domain data, of out-of-domain data, what we do is we take USM trained on YouTube and report it on 3 tasks. The first one is Chorale, that is African American Vernacular English. The second is Speech Stew. This is public available speech recognition data like AMI, Broadcast News, Common Voice, Switchboard. And the third is Floors. This is a 62-language multilingual data set to see how well we do in sort of low resource or unseen languages. And the blue is USM, and the yellow is Whisper. And what you can see here is that the model is much better than Whisper on all of the 3 tasks. And furthermore, if you do some in-domain training, which is the yellow, you can see this further helps which is blue, this further helps the performance. What this basically shows is that our massive model that's trained on just YouTube data to do speech recognition is able to generalize well to other tasks because of the size of the model and the amount of data we use. And another nice thing is that the larger models can serve as a general backbone for downstream tasks. So to demonstrate this, we looked at Kovos, which is a translation data set. And here, high, middle, and low corresponds to sort of languages that are commonly translated, and low is languages that are incommonly translated. So what we did here is we took Whisper, and we also took USM that is fine-tuned to do some translation, but a small amount of data we fine-tuned on. So we segment it into high, medium, low based on resource availability. And here we calculate a blue score. So there, higher is better. And what you can see is the USM outperforms Whisper for all of these tasks. So the models shown so far, we gave the model a hint as to what language is spoken. But here's a demo where you can run a universal speech model where you don't give the model any hint of what is spoken. You can see actually the model is generalized to do code switching now too, even though we've never trained it like that. So here's a demo on that.
Play Hua Mulan on living room TV. Text mom， 我下午4点去接你。Text dad， 不要忘了明天的太极拳课。在厨房音箱上播放 Justin Bieber。
Okay, so massively multilingual models like USM extend this on-device work. They make our models able to more natively handle more languages within one model. You can see that the USM has sort of state-of-the-art performance in speech recognition and translation. But one of the challenges here is that these models cannot handle audio-to-X tasks, doing things like summarization and question-answer. So let me move and quickly talk about what we're doing in Project Gemini. So the goal here of Project Gemini is to, instead of building a massively multilingual model to do just speech recognition, people are transitioning over to having multimodal language models that take text, image, and audio as input and emit text and image as output. So for audio, what we did is we trained the models on very similar data, translation and speech, YouTube data that the USM is trained on. But now the whole process has additional text and vision components as well. And so if we look at those same metrics I was showing before, for both speech recognition and translation, the first column is that USM, the second is Whisper, and the third is what we call Gemini Nano and Pro. These are two different variants of the model. Nano is around 20 billion parameters, and Gemini 20 billion active parameters, and Gemini Pro is around 141 billion active parameters. And you can see the Gemini Pro model is also state-of-the-art in both speech recognition and translation. But more importantly, Gemini can do these audio-to-X tasks, and I'm going to show some demos in the next few slides. So again, the model is not actually trained to do any of these tasks. It's really just trained to do speech recognition and translation and next step and sort of next token perplexity. But a lot of these capabilities are now unlocked in the model by just having the model be a lot larger and also training with the vision and the text. So for the unlike other language models that rely on speech-to-text conversion, Gemini can process raw audio signals directly. So this can allow it to capture nuances like voice tone and emotion and pronunciation that are often lost in the transcript. So let's take a look at this video.
How to pronounce the word Lunar January in Chinese? Option A, 正月. Option B, 正月. Which one is correct? Which tone is the correct tone for the first character?
Option A, the first character is pronounced with the first tone.
Okay. Second is, Gemini seamlessly integrates audio with other modalities like vision and text. So this enables it to understand the context of a situation pretty comprehensively and report accordingly. So for example, it can analyze audio and image simultaneously and answer questions about a scene, even though it's never actually trained like this. What's the first step to make a veggie omelet with these ingredients?
Crack the eggs into a bowl and whisk them.
Thank you for the instructions. I've started making my omelet. Does it look ready now?
It looks like it's almost ready. you can flip it over to cook the other side.
Why is it not ready?
It's not ready because the eggs are still running.
What about now?
It looks ready now. You can take it off the heat and serve it.
Okay, and finally, Gemini can process and understand audio in multiple languages. So this makes it a really valuable tool for communication access and information across various linguistic barriers.
Alors Pierre, quelles sont les couleurs incontournables de la saison?
Eh bien Marc, cette saison, le jaune canari et le rouge écarlate sont à la mode. Mais le bleu nuit est out.
Hi, Gemini. I don't understand this podcast. Can you please summarize it for me in English?
The podcast is about the colors that are in fashion this season. The colors that are in fashion this season are canary yellow and scarlet red. The color that is not in fashion this season is night blue.
So you can see that I didn't even have to tell it, this is French. It was automatically able to detect that and translate it. So this is basically what the focus of our team is. And yeah, I think that concludes our talk. Happy to answer questions.
Hello, thank you for the talk. So I just have a question. Thus, you have presented many technical advancements that's made in Google to push state-of-the-art in speech recognitions. So I wonder, what do you think is the most important technical contribution from Google, apart from the transformer, that's fundamentally change the way we do speech recognitions from your point of view? Thank you.
So we have been one of the first, there has been also work from Microsoft and many other companies that we should also give them a lot of credit for, but we have been one of the first to sort of put all of these components and stick it on device, showing that it has the quality that it can have at a fraction of the size of the conventional model. And I think that's to date, that has been one of the biggest contributions. That's not just one specific thing, it's a lot of people. And again, I'll say many other companies have done that, and of course we should, make sure we give credit and be aware of that too. Yeah, and now the challenge is really extending all this towards our large language model era and seeing what audio to X capabilities can be unlocked with the model.
Thank you for the great talk. I was particularly interested by the history you gave. It was really great and very clear. And I was wondering, every time you have a new innovation, you seem to have a lot of them every year. You produce a lot of new tools. And maybe sometime the whole features is less than the sum of their part. So I was wondering how you make the decision to decide to move on. Okay, this is a feature that we need to build upon, because everyone, I guess, is a trade-off. That must be a very difficult process. I was wondering what was your process.
Yeah, that's a good question. So pretty much whenever we release a model, there's always some big issue, right? The long tail phrases are not good. So it's really a collection of talking to our execs and seeing what the feedback is and where's the big 2 or 3 areas that we really need to improve going forward. And that sort of indicates what the focus should be for the next year or two. It's really just, where are we now? Where do we see ourselves on the roadmap? Where's the model not doing well? And then how do we target improving that? That's sort of a collection of, decisions that are made across the company from many people and their advice.
Hello. First of all, thanks for the talk. And the results you showed are mostly for the rich resource languages. What do you suggest about the languages which doesn't have these kind of which are very low in resource, whether they don't have the TTS yet, or they don't have the ASR systems yet, or they don't have the digital form? how do you suggest that we can reach to this level in the low resource language?
Yeah, that's another good question. So, we have seen that with these massive models, the models, even if you train them on 75 languages, they are able to show better performance in unseen languages like I showed in Floors. Obviously, having more in-domain data helps, but just based on the sheer size of the models now and how they're able to generalize, they are doing better in lower resource languages. We are also looking at techniques, of course, to mine more data from other languages and add them in.
Do you have any, sorry, one more question. Do you have any suggestion where you don't have basically the data in the textual form, you only have the audio form? So without labeling and all the stuff, how do you suggest that we can improve those kind of systems like into ASR and into TTS systems?
So one thing we're seeing is that there's sort of two phases to training. There's what we call a pre-training phase, and then there's a post-training phase. And so one way to do this is to just take a very small amount of labeled data and the domain you want. You don't need a lot, probably 100 utterances, I think should be fine, 100 to 500, and just fine-tune the model on that and see if that will get you the quality. Because a lot of it, you might get some quality, let's say on some completely unseen language, the word error rate might be, even though you haven't seen it, I'm pulling numbers from the top of my head, might be 20%. It is possible that if you just find post-train this on a small amount of high-quality data, that might unlock the capability that you want.
Thank you.
Yeah.
Yeah, thank you for the incredible talk. I have two questions. The first is kind of related to the previous question. So I also work in low resource settings, and end-to-end models, or rather like something like self-supervised models, have better data economy. So you can use untranscribed audio, you can use text to fine-tune the language model, and then you can just use a small amount of transcribed data. So how, in your opinion, can end-to-end models have better data economy to utilize low resource settings?
How can they have better data what?
Data economy. So, for example, utilize untranscribed data or just text without audio.
So I should say the models here are trained with what they call wave to vec, right? So you take a bunch of unsupervised data, you pre-train your audio encoder with that, and then you do supervised fine-tuning. So we are doing that inherently in the training. What we're not doing right now is we're not training that jointly. So what we do is we first do the unsupervised pre-training, and then we do the fine-tuning, because we haven't really seen any difference in quality by doing the two optimizations together. But we do a pre-training with a bunch of unsupervised data.
But
Yeah.
then Wave2Vec does not have a language model. It needs an external language model to do beam search, right?
So the way this is done is you train you train your speech encoder on Wave2Vec, and then you train it supervised with the ASR data, and then you take the big LLM that is also trained with vision and text, and you train the full LLM with all three modalities together. Now, is this absolutely the best on low resource languages? No, but we are seeing that generalizes. I think there's two ways to improve the low resource language setting. One is you just add more data into unsupervised pre-training, or you add more data, labeled data, into the supervised training. But I do think, we are seeing a lot of capabilities do inherently end up being unlocked in the data, just given the size. So it's possible we have a lot of text data in some language, but we don't have a lot of audio data. So if you just post-train on a little bit of data, it would be worth checking if that just unlocks what you need to. To give you an idea, like that audio-visual example you saw, the model is not trained on audio-visual pairs at that point in time. It's trained on, the audio part is just trained to do speech recognition and translation. It's not even trained to do summarization, right? And we definitely did not train on any audio-visual speech recognition. But we did see that inherently the model has the ability to do this. And if you post-train on a little bit of data, it gets even better. And when I mean little bit, I mean just a couple hundred examples, not a lot. So that's what I would check for low resource language first.
Yeah, that's incredible. Thank you.
Yeah.
Okay, hi. First of all, of course, thanks for the talk. I would be interested if you could elaborate on how you go about continuously assessing the accuracy of the model once you have put it into production. So if, for example, for the end customer, the model makes a mistake, How do you assess that? How can you actually detect errors or areas of improvements where you can still modify the model to deliver a better service?
Yeah, so people submit bugs if the model's not doing well. We often get bugs during the presidential elections when it's not detecting certain candidates. So once we have bugs, then the question becomes, how do we fix this model, right? Let's say you want to fix even the USM or any of those on-device models. It's not a simple spot fix, right? Because you have to retrain the model. So that's not something you can do in a day. So spot fixing is a very important component. And typically you do that with this contextual biasing thing. So you might, training the FST is just counting. So it's really easy to add additional terms that you're not detecting well into this and retrain the FST. That can be done instantaneously. And that's a very common way we do spot fixing. If we see inherent issues in the model. So one is that when Pixel 6 was launched, we launched it in November, and December 1st, we get an email that the model is hallucinating words. And this is because the model was, when the model was trained in background speech, the background noise was transcribed. And so then we had to add in a little bit of additional data to fix the hallucination issue. So it depends on what the bug is. We try to fix most things with spot training, or with spot fixing. If we have to inherently retrain, we do, in a way that we can do it quickly. But there's places you can report bugs, and people do that.
Okay, thank you.
Mm-hmm.
So I'm a little curious, actually, if there have been any efforts on your team similar to the Deep Dream efforts that kind of tried to pick up somehow, get some insights on internally how the model is representing all the data, if there was something analogous in your department?
So we have done this like years ago, not recently. So when neural networks first started being used in speech recognition and everybody was saying, okay, this is a black box, we did some analysis showing like what the network is learning in every layer. So effectively what we did is we took the outputs out of every layer, mapped them to did some PCA to map it to some low dimensional representation and plotted it. And what you typically see is that like the lower layers are basically taking speech from different speakers and grouping them together, and the higher layers are then discriminating between different phonemes, getting ready to do classification. This was done 2009. It was not done recently. Recently, we haven't done anything like that.
Okay, I was just
it's a really good question. I mean, yes, we are pouring, hundreds of millions of hours into this model. We are measuring metrics. But we don't have good ideas of, we haven't done a lot of analysis on this.
I was also just curious if there was some weird audio distortions of some signal that I could listen to later.
But speaking of what the model's doing, the hardest thing right now for us is we're really after these audio to X tasks. And how do you have a good way to evaluate audio to X tasks? Because think about like question answer, right? So you have to run human evaluations in order to do that. So that's been a big challenge, is we train the model to do ASR and AST and next token perplexity. So those are the metrics we evaluate in training, but they're not actually correlated to what we want to do with these models. And the only way to evaluate that in the end is to do human evals. So that adds to the time, right, to figure out what's the right metric that we want.
Yeah, all right, thank you. Very impressive.
Souvenir from the organizers.
Oh, thank you very much.
Chocolate from Leon.
Thank you so much.
Thank you.
Yeah.
Then we feel less useless,